Hi! In this video we're going to learn about integrals of the exponential function. In order for that to be meaningful, let's do a little bit of review so that you feel really comfortable with the exponential function. Okay, so the very first thing for review is the value of e to the 0 is equal to 1. Keep in mind that when the exponent is equal to 0, no matter what the base is, the answer is 1. 3 to the 0 is 1, 4 to the 0 is 1. E is a number, transcendental number, approximately 2.718. When you raise that to the 0, it equals 1, just like every other number. Okay, so that actually cuts up the number line into two separate categories. Here's e to the 0, which is equal to 1, right? E to the 0. So if I raise e to a negative number, a number that's less than 0, I get a number that's less than 1. If I raise e to a positive number, then I'm going to get a number out that's greater than 1. I've also shown these inside some graphs here. Here we can see that for positive values of x, whether we get exponential decay or exponential growth simply depends on whether the exponent a is positive or negative. Okay, so assuming that the x is positive in a function like e to the ax, here this is a function e to the ax right here, and again right here this is the function e to the ax. Okay, if x is a positive number but a is a negative number, that means e to a negative number will be less than 1. So here's the number 1, that's the y-intercept, and you can see that when x is positive, it's going down, down, down. That's why we call it exponential decay when this a, which we call the growth rate, is a negative number. Okay, contrary-wise, if a is a positive number, then that number is going to be greater than 1 when x is positive. And so here again is the y-intercept of 1, but then it goes up, 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 and it keeps getting bigger and bigger, and that's called exponential growth. These are the two types of behaviors that you would expect to see depending on your growth rate. Okay, the other thing you'd like to note on this picture is that e to any number a is never equal to 0. Take a look at both of these graphs. Do you see any x-intercepts on these graphs? Any places for x values such that the output is equal to 0? It never intersects the x-axis here, and this one is going up all the way, so it's never going to intersect the x-axis either. So the important thing to know is that an expression of the form e to the a is positive for all values of a. It doesn't matter if the exponent is negative or the exponent is positive, the output will always be a number that's greater than 0. Why would I care so much about that? Well, do you ever remember previously in this class when we started solving equations equal 0, and then those would be special points? Remember? When we were looking for the relative mins and maxes, the critical points were the places where the derivative was equal to 0. But what I'm saying here is that if your derivative is of the form e to the x, it will never equal 0. So you're not going to have any critical points. And that kind of makes sense because if you look at the graphs, these graphs don't have any peaks or troughs. Either it's going down forever or it's going up forever. Okay? But that's on the total function, of course. The thing is, the derivative of a function of the type e to the x is also of the form e to the x. So the derivative of an exponential is another exponential. Now let's go through this equation where in the exponent here we have a times x. Keep in mind that a is the growth rate. Remember, if a is positive, it will be going up. If a is negative, it's going to be decaying down. So whether a is positive or negative is pretty important. The value of a is very important. Okay, so if we take the derivative of e to the ax here, the derivative of e to the x is e to the x. So the derivative of e to the ax is e to the ax. But then using the chain rule, we have to multiply by the derivative of the inside function. Here the inside function is the function that's located in the exponent, which is ax, so the derivative is a. That's where that a comes from. Usually we like to put it out in front, so the derivative of e to the ax is a e to the ax. Notice that the growth rate on the derivative is also a, same as the original function. Now what do you think the integral is going to be? Remember, the integral, the antiderivative, is the opposite of the derivative. So if I have to integrate this function e to the ax, since the derivative of e to the ax is a e to the ax, the integral should be e to the ax divided by a. Why is that? Well, maybe let's do a quick check so you can see that it's true, and then we can think about it. Let's take a check by taking the thing that I claim is the antiderivative, e to the ax over a. Take the derivative of that, okay? Constant multiple rule, I'm going to pull the 1 over a out. Then I'm going to take the derivative of e to the ax. And actually I have that written right up here. You see the derivative of e to the ax is a e to the ax. Okay, I've still got that 1 over a out in front. And the derivative is equal to e to the ax times a. And lo and behold, the a cancels with the 1 over a. That's why that 1 over a was put in place there when we find out that the integral of e to the ax is e to the ax over a. So this a cancels with that, and you get e to the ax, and that's exactly what you were asked to integrate. Okay, so the other way to see this rule, instead of just memorizing it, would be for you to perform a u substitution on this integral. I'd like you to do that separately just to review u substitution, and in the next video, when I'm going through the examples, I will do that on the specific examples. Okay? Here, there is an inside function and an outside function, just like up here. The inside function is ax. So here, the inside function is ax. So for your u substitution, you should let u equal to ax. Alright, then if you go through the u substitution, you'll see that you have to end up dividing out by a to match the du and the dx, and that's where the 1 over a comes from. Okay, like I said before, a is the growth rate. This is really the thing that describes the behavior of the function all in all, because it decides whether it's decay or it's growth, and it also decides the rate at which that's happening. Is it decaying really fast, or is it decaying sort of slow? Is it growing really fast, or is it just growing slowly? That's all determined by the value of a, the growth rate. And an important thing to note is that when you have a function of the form e to the ax, where a is a number, that function and its derivative and its integral will all have the same growth rate, a.